Good morning, children. Today we'll try to cover all topics from chapter solutions. After completing this, please solve the previous year questions also. That will give you a good practice. Okay, now let's begin with it. Solutions. So what are solutions? Solutions are homogeneous mixture. Homogeneous means you cannot distinguish between what is the solute and solvent in it. It's a homogeneous mixture of two or more components. Usually we talk about two components. So two components means if there are two components, we call such solutions as binary solutions. Okay, and in a binary solution, two components are there. One is solute, the one that is present in less amount. Solute is present in less amount and solvent is present in more amount. Okay, if suppose I dissolve sand and water, I can distinguish where is sand and where is water. That's a heterogeneous mixture. The solution, for example, if I dissolve salt in water, common salt in water, or any soluble salts in water, sugar in water, they'll form a homogeneous mixture. So solutions are homogeneous mixture of two or more components. There can be more than two components also in it, right? So we will usually talk about a binary solution in this chapter. Okay. Now let's move on to the types of solutions. There are various types of solutions based upon what is a solute and solvent in them. For example, if the solvent is gas, the name given gaseous solution is on the basis of what is a solvent in it. If the solvent is gas, we call it as a gaseous solutions. Okay, in the gas solution, the solute can be either a gas, it can be liquid, or it can be solid. So we call them as gas in gas, liquid in gas, solid in gas. So the solvent is gas, we call it as gaseous solutions. So you have some examples for it. Gas in gas is mixture of nitrogen, oxygen, or any gases. Yeah. So liquid in gas, chloroform vapors when mixed with nitrogen. Okay. Then you have a solid in gas. Solid in gas, camphor. Okay. So all sublimable substances, they get dissolved in air. Right. Liquid solution. Liquid solutions, as I told you, what will be the solvent in them? Liquid is the solvent. Right, so you again can have a solute as gas, liquid, solid. Gas in liquid, we usually call solute first. So we call it as gas in liquid type. So that example is oxygen when dissolved in water, liquid in liquid, ethanol in water, alcohol is soluble in water, though covalent, soluble because of intermolecular hydrogen bonding. Solid in liquid, sugar in water, glucose in water. Okay, that is sucrose. Sucrose is basically sugar. Then you have solid solutions. Solid solutions are those in which the solvent is solid. Right. So you can again have solute as gas, liquid, solid. Gas in solid is hydrogen and palladium when it is adsorbed in this thing, palladium. Liquid in solid, amalgam of mercury with sodium. Solid in solid, alloys, that is copper dissolved in gold. So you can have all alloys, These are the examples, the types of solutions. Now let's move on to the different methods of expressing the concentrations of solutions. The first one is mass by mass percentage. Mass by mass percentage, W by M, or you can also write it as W by W percent. W by W percent. That means both we talk about in terms of mass. That means the mass of a solute that is dissolved in 100 grams of, it is grams, 100 grams of the solution. Okay, so it is mass of the solute dissolved in 100 grams of the solution. That is mass by mass percent, usually written as W by W percentage. Okay, so the formula is mass of the component divided by total mass of the solution. In a way, if we want, we can write the formula as W by W percentage is equal to weight of the solute divided by weight of solute plus weight of solvent into 100. Small letters I have written for solute, capital letter for the solvent. Okay, so mass of the solute dissolved in 100 grams of solution. For example, if I say 20%, it's weight by weight, 20% weight by weight NaCl solution. What do we mean by this? 20 grams of NaCl is dissolved in 100 grams of solution. So for both solute solvent, we talk in terms of grams. Volume percentage, V by V percent. This can be also represented as volume by volume percent, which is written as volume of the solute divided by volume of solute plus volume of solvent into 100. For percentage, we write 100. There is one example given in NCERT, that is 35% volume by volume solution of ethylene glycol. It's one of the application mentioned there. Like this much percentage volume by volume ethylene glycol. It's used as an antifreeze in the cars, that is cooling the engines. Okay, at this temperature, it lowers the freezing point to around minus 17.6 degrees Celsius. Okay, so you should just have an idea about it. Then you have mass by volume percent. Means for the solute we talk in terms of mass, and for the solution you're dissolving it in liquid form. So you can define it as mass of the solute dissolved in 100 ml of the solution. In 100 ml you are dissolving. For example, the same, if I say weight 20% NaCl, it's weight by volume given. So you will say 20 grams NaCl is dissolved in 100 ml solution. So for solute in terms of mass, and you are dissolving in liquid solvent, and total is, the volume is to be written in 100, right? Next, you have ppm. Okay, next we have ppm. ppm is number of parts of all the components divided by total number of parts of all the components into 10 to the power 6. Okay, parts of one component divided by total number of parts of all the components into 10 to the power 6. Okay, so suppose I have 5 ppm. I am saying 5 ppm. Say calcium chloride is there in water. It's there in water. It means 5 grams, if I talk in terms of grams, of calcium chloride is there in 10 to the power 6 grams of the solution. Okay, for that I am talking, for whatever is mentioned here, that is for the solute mentioned, right? And for the solution it will be 10 to the power 6 in ppm. Next we have is mole fraction. Mole fraction is represented with the symbol chi, and it is defined as, it's a ratio of the number of moles of one component divided by total number of moles of all the components. Suppose there are two components 1 and 2, and their number of moles are N1 and N2. You will have the mole fraction of the first component as number of moles of one component divided by number of moles of both the components. This is mole fraction. Similarly, the second mole fraction would be written as number of moles of the second component divided by sum of moles of both the components, and it has no units, children. This has no units. Okay, another thing is the sum of the mole fractions of both the components is 1. It is 1. Okay, so let's move to the next one now. Molarity. Capital M is the symbol for it. It's defined as number of moles of the solute dissolved in 1 liter of the solution. 1 liter of solution. Here you talk about solution, and the units for this is moles per liter. We can write the formula as molarity is number of moles by volume in liter. Listen children, if the volume is given in ml, you have to divide by 1000 so as to convert into liters. In case it's given in liter directly, you will just write weight by molecular weight into 1 by volume in liters. This is about molarity. Here you also have one more formula which is required, in the numericals, the dilution formula. The dilution formula is M1V1 is equal to M2V2. There are some numericals in NCERT wherein the dilution formula is required. Okay. So next you have is molality. Molality symbol is small m. It's defined as number of moles of the solute present in 1 kg of the solvent. Here you talk about weight of the solvent. It's 1 kg of solvent. And the unit for molality is moles per kg. The molality can be written as number of moles of the solute by mass of solvent in kilograms. So if it is given in kilograms, you will be writing directly weight by molecular weight is moles into 1 by weight in kg. So in case it's given in grams, you'll divide by 1000 and calculate the molality. Right? Now there are some methods like mass percentage, ppm, mole fraction, molality. These are all independent of temperature because they all involve weight. Right? Whereas molarity is a function of temperature. Even, in this we could have taken in the second one, the one which is dependent on temperature, volume by volume percentage. Okay, so they are all dependent on temperature because they all involve volume, and the volume depends on temperature, mass does not. Is it clear? Listen children, there are some numericals in your textbook like calculate molarity and mole fraction. If the percentage is given and the density is given. To solve such questions, what you will do is, you will be, this mass percentage means weight of solute is, that small w is given as 20 grams. And the mass of solution is 100. So capital W is given, 100 minus 820, that will be 80. So you have the weight of solute, weight of solvent. Both you have. So molality can be calculated easily. Given weight by molecular weight into 1000 divided by weight in grams. So weight is 20 and molecular weight of Ki you are going to put, which is the solute present here, and the weight of the solvent in this case is 80 because the solvent weight is there. So this is one molality calculated. So we have individually the mass of solute and solvent. We can also calculate the mole fraction in this case. So mole fraction will be the weight, the number of moles, right? The weight of solute divided by the molecular weight of Ki. You can just add up the molar masses. Molecular weight of Ki, 39 by whatever is the molar mass of iodide, I think 127. So similarly, weight divided by the molecular weight of Ki plus 80 divided by water, molar mass is 18. So you'll calculate the mole fractions. That's the second part done. The third part is molarity. Molarity is given weight by molecular weight, so 20 divided by the molar weight of Ki into 1000 divided by volume in ml. Volume mass of the solution is 100 because 20% was given. 20%. So mass of solution is 100. Divide mass by density. Density is given as 1.202. So 1.202. So mass by density. So that means you have calculated volume. So all three can be calculated. This was slightly different questions, so I discussed it. Others are simple where you have to directly put in the formulas, right? Okay, now we move on to the next topic, that is solubility. Solubility is defined as the maximum amount of the solute that can be dissolved in the specific quantity of a solvent at a specific temperature. Means the solvent amount is fixed. In that fixed amount of the solvent, at what temperature you are able to dissolve the maximum amount of the solute. Obviously, when you change the temperature, the amount of the solute will change. If you change the amount of the solvent, also it will change. Right? So there are two concepts we have to take here. Solubility of solid in liquid and gas in liquid. The first I'm taking solid in liquid. So the factors which affect its solubility are, number one is like dissolves like. Means polar will dissolve in polar solvents, non-polar in non-polar solvents. Right? Ionic in ionic, covalent in organic solvents. The next term which we have here is saturated unsaturated solutions. Saturated solution which cannot take in more of the solute at particular temperature and pressure. Right? So it cannot take in more quantity, it is saturated. Unsaturated in which more solute can be dissolved. Can be dissolved at the same temperature. Okay, now there are two factors in it, temperature and pressure. So temperature, you'll have to talk about general aspect. If I say most of the cases, you increase the temperature, the solubility of solid and liquid will increase. Until unless it's endo or exothermic. If it is endothermic, solubility will increase by increasing temperature. Okay, in endothermic cases, solubility increases with increase in temperature. And if it is exothermic, solubility will decrease with increase in temperature as per Le Chatelier's principle. We'll have to talk about Le Chatelier's principle in this. Is this clear? And in case of, the solid and liquid, pressure has no effect, because solids are those which are already incompressible. So there is no effect of pressure on the solubility of solid and liquid. And now let's talk about solubility of gas in liquid. So gases are generally soluble in water. Okay, so then they have given like oxygen. That depends on the nature of the gas also. HCl is very highly soluble, oxygen slightly soluble, right? So this is the main, the factor in gas and liquid, that is effect of pressure. So it's like solubility of the gases increases with increase in pressure. With respect to this, there is a law. It's Henry's law. Henry's law, very important, children. It says solubility of a gas in liquid is directly proportional to the partial pressure of the gas above the surface of the solution. Or in other words, you can also say the mole fraction of the gas is proportional to the partial pressure of the gas over the solution. Pressure is over the solution, gas is dissolving in. So mole fraction is in the solution, partial pressure is over the solution. So with respect to this, there is a statement, formula for it. The formula for Henry's law is partial pressure is equal to Kh into chi, where P is the partial pressure of the gas over the solution, chi is mole fraction of the gas in the solution, Kh is Henry's law constant. It is constant, and this constant depends upon temperature and the nature of the gas. What temperature and the nature of the gas? Kh is directly proportional to temperature. More the temperature, the Kh increases. And Kh is inversely proportional to solubility. Very important aspect, children. You can check for the table given in NCERT. It says, just check for helium, it's fine. Nitrogen. Two different temperatures, the Kh value is given. Lower temperature, the Kh value is this. More the temperature, Kh increases. Same way for oxygen and for others also. Kh is inversely proportional to solubility. Right? Sometimes, suppose I say, a question can be asked. At one particular temperature, they give the Kh values of different gases. So how will you select which is more soluble? More the Kh value, lesser will be the solubility. Least Kh value, more will be the solubility. Is this clear? Now let's move on to the next thing. The graph is there. It's for Henry's law only. Between mole fraction and the partial pressure, it is directly related. Right? So next you have temperature effect. How temperature affects the solubility of gas and liquid. Minded children, solubility of gas and liquid is an exothermic process. So exothermic process means more gases will be soluble at lower temperature. For this, there is one reason question given, that aquatic species are more comfortable in cold water than in warm waters, because solubility is more at lower temperature. Okay, so if the temperature increases, the solubility of oxygen in water will be less. So the amount of the oxygen dissolved in water become less, means aquatic animals become uncomfortable. They will be more comfortable in cold water than in warm water, because in cold water more quantity of oxygen is soluble, whereas in warm water the amount of the oxygen dissolved in water decreases. Okay. Next, we move on to the applications of Henry's law. The first application is the cold drinks. Okay, in soft drinks, carbon dioxide is dissolved in them at high pressure. The solubility of CO2 is more at high pressure. That's why when we open the bottle, the carbon dioxide escapes out with the fizz. The second application is the scuba divers. Scuba divers, they cope up with the high concentration of dissolved gases. They cope up with the high concentration of dissolved gases while breathing in air. So the thing is, when they move inside, the pressure increases. When the scuba divers go inside, the pressure increases. So solubility of the gases in the blood increases. So more amount of the air has gone in their blood. So when they come up, that excess of oxygen and nitrogen which has gone into the blood is not able to come out. So which causes a peculiar condition in them. That is bends. and it's painful and dangerous to life. So it's basically the nitrogen bubbles are formed in their blood. This blocks their blood capillaries and creates that medical condition. Now, how do they avoid it? To avoid the bends, and the harmful effects of the nitrogen in the blood, the air which they carry is diluted with helium, that's 11.7%, nitrogen 56.2%, and oxygen 32.1%. So helium, you checked in the tabular column previously that helium has high KH value. So when helium has more KH value, the solubility will be less. Okay, so helium is less soluble, so that is better for them. Nitrogen amount is reduced because nitrogen KH was less, its solubility was more. Okay, the next application is at the high altitudes, the pressure become less. So when the climbers, they go up, they climb up the mountain, because of the low concentration of oxygen, okay, they are unable to think, they become weak, they are unable to think. That is a medical condition called anoxia. So because the pressure is low, the amount of the air which gets dissolved in their blood also decreases. That makes them, feel weak and they're unable to think. Fine. Next is the vapor pressure of the liquid. Now for this, there is a Raoult's law. First let's talk about it, then I'll explain with the graph. Raoult's law says that the partial vapor pressure of each component is directly proportional to the mole fraction present in the solution. It's basically the reverse of Henry's law. Henry's law says the gas from here gets dissolved in the liquid. And Raoult's law says gas, if it is more present here in the solution, more amount of the pressure will be created. So both go in the opposite direction. If this is a container, Henry's law says more the pressure here, more will be the mole fraction dissolved inside. And the Raoult's law says more the mole fraction present here, more will be the pressure created. So it says the partial vapor pressure is directly proportional to the mole fraction present in the solution. So if there are two components in it, 1 and 2, their partial pressures are P1 and P2. So we can have P1 is equal to, this is one formula children, P1 is P1 naught chi 1, where P1 naught is the vapor pressure of the pure component when I take only one component in that particular container. P2 is P2 naught into chi 2. So if I take both the components, then their pressure becomes partial. If I take one container and only one component in it, its pressure will be referred to as naught. If it is first component, P1 naught. If it is second component, P2 naught. And if in that same container now, I take both the components. So both the components mean the pressure created by them will not be their own pressure. It will be the partial pressure. Means whatever is the total pressure will be the sum of both. So we will call that as P is equal to, I'll write here, P is equal to P1 plus P2. That means the partial pressure of the first component plus the partial pressure of the second component. And their values if I put, I will get that formula P is equal to P1 naught chi 1 plus P2 naught chi 2. This is the total pressure. Okay. Now this I have just told you here that Henry's law and Raoult's law, Raoult's is a special case of Henry's law. Raoult's law is saying P1 is equal to P1 naught chi 1 and Henry's law says P is equal to KH into chi. So if you compare them, we can say here that the KH and P1 naught, these are the only differences in them. So we can say that the Raoult's law becomes a special case of Henry's law if the KH and P1 naught become equal. Fine? Okay. Now ideal solution. Ideal solutions are those which obey Raoult's law over entire range of concentration. They obey the Raoult's law. That statement which we wrote the formula there. P is equal to P1 naught chi 1 plus P2 naught chi 2. Okay. And another thing, for ideal solutions we say delta H mixing is equal to delta V mixing. I'm sorry, delta H mixing is 0, delta V mixing is 0. In a way, we say that the interactions before mixing and after mixing are equal. So, suppose you are mixing solute and solvent. So, after mixing them, the whatever the interaction between solute and solvent, they are of the same order as the interaction between solute and solvent. So, no new bonds are formed, no bonds are broken. So, we say delta H mixing is 0. And delta V mixing is also 0, because in such cases we say 10 ml of the solute if I mix with 10 ml of the solvent, the total volume will be 20 ml. The volume will be the sum of the solute and solvent. If it becomes more and less, that is a case of non-ideal solution. Got it? And there are some examples for it. Normal hexane, normal heptane, one example. Second, bromoethane, chloroethane. Third example, benzene and toluene. Okay, so this is a graph for the ideal solution. This side vapor pressure, the mole fraction, and this side I am taking first component. Say I am representing as 1 or A, whatever you can write. So if it is mole fraction 1, that is maximum. A is 1, B will be 0. So the pressure will be only because of A, that is referred to as PA naught now. And if I start from here, this is B1 and A mole fraction is 0. So 1 means chi B is 1, that means the pressure is only because of B, that is PB naught. So this way if I go, the pressure decreases, even this way it decreases. Along this line it's represented as PA, it's no longer PA naught now, it's PA is PB, PA naught into chi A. On this line, PB, that's a partial pressure of B, which is equal to PB naught into chi B. Right? On this line, it's the total pressure. That is the sum of the partial pressures of both the components. I hope till here it is clear. Now children, non-ideal solution. Solutions which do not obey Raoult's law over entire range of the concentrations are called as non-ideal solutions. There are two types. The first, we are taking non-ideal solution showing positive deviation. You can remember like this, for positive deviation everything is positive. Everything positive means delta H mixing is positive, delta V mixing is positive. In a way, if I mix 10 ml of a solute with 10 ml of solvent, the volume becomes more than 20 ml. Volume will be more than 20 ml. Okay, why it is more? Because the interactions after mixing are becoming lesser. It's given here. The interactions are becoming lesser. So positive means they will be now moving far away. Means whatever bonds were there, they are broken. Broken means delta H mixing is also positive in them. So with the graph also I'll explain. Let me just talk about their example. Ethanol and acetone. One example of positive deviation. Carbon disulfide and acetone. The second example. Yeah, beta, this is the example for positive deviation, vapor pressure and mole fraction. First component this side. So if I am writing A here, it should be chi A1. Chi A is 1. So it's PA naught. B is 0. This side chi B is 1. Chi A will be 0. So if corresponding B is maximum, so its pressure will be PB naught. This way it's PB, this way it's PA, and the sum is PA plus PB. And all the curves are above. The straight line was for an ideal solution. For a non-ideal solution, all the curves are positive. Means the pressure is more. Interactions have weakened, that's why the vapor pressure becomes more. And already I told you for positive, everything is positive. Right? Now we'll move on to the non-ideal solution showing negative deviation. Negative deviation, everything is negative. Delta H mixing is negative, delta V mixing is negative. Negative means the pressure becomes less. That means the interactions become more. Solute-solvent interactions are more than the solute-solute and solvent-solvent interactions. Means after mixing them, the molecules come closer. When they come closer, means the forces become more. Right? The bonds are formed. Bonds are formed means it's exothermic process. So delta H mixing was negative. You have example phenol and aniline, negative deviation, chloroform acetone. So here we can explain chloroform CH, you have CHCl3, and if you mix it with acetone, there is force of attraction, intermolecular hydrogen bonding exists between H of chloroform and O of acetone. So bond is being formed between them. So force of attraction is developed, right? Formation of bond is exothermic, so it's exothermic. And if you talk about the graph, vapor pressure and mole fraction, same way, this side is A, chi A is 1, chi B is 0, PA naught. Chi B is 1, chi A 0, PB naught. This way chi PB, this way PA, and the total pressure is PA plus PB. PA, PB children are the partial vapor pressures of A and B. And PA and PB are the partial vapor pressures. PA naught and PB naught are the pressures of the pure components. If I write naught, that is for pure component. PA and PB are partial. Is this clear? Okay. Next is azeotropes. Azeotropes are those binary mixtures which have the same composition in the liquid phase and the vapor phase. In the liquid phase and vapor phase, they boil at constant temperature. That's why children, we also call them as constant boiling mixtures. That means if I take a mixture in some percentage, there are two components in this A and B, they'll vaporize together, they will condense together. Okay, so they are saying they'll have a same composition. Means whatever mole fraction I take here, in the vapor phase also the mole fraction remains the same. Yeah, it was not visible. Just see, if whatever mole fraction they were mixed before, in the vapor phase also their mole fraction remains the same, then it's a azeotropic mixture, which have same composition in the liquid and the vapor phase. Right? And they cannot be separated by fractional distillation. Since they boil together, you cannot separate them by fractional distillation. Now, they are also of two types, minimum boiling azeotrope and maximum boiling azeotrope. Minimum boiling, as the name itself says, boiling point is minimum. Boiling point is minimum means they will have more vapor pressure. If the boiling point is less, means vapor pressure is more. So the non-ideal solutions showing positive deviation, they form minimum boiling azeotrope. From the name itself you can make out. Minimum boiling means the vapor pressure is more. So more vapor pressure means non-ideal solutions showing positive deviation will form minimum boiling azeotropes. Example children, ethanol water mixture, wherein 95% ethanol, if it is there in water, you will have minimum boiling azeotrope. Got it? Next is children, maximum boiling azeotrope. The name itself says maximum boiling means maximum boiling point is more. More the boiling point means vapor pressure will be less, because boiling point is inversely proportional to the vapor pressure. It's inversely proportional to the vapor pressure. So maximum boiling means those non-ideal solutions which show negative deviation, they form maximum boiling azeotropes. Examples for this children, it's like nitric acid and water, 68% nitric acid with 32% water. That forms a maximum boiling azeotrope. Okay. Then we move on to the next topic children, that is colligative property. Now what's a colligative property? Properties which depend upon the number of the solute particles, not on their nature. These are called as colligative properties. We have 4 colligative properties to study in this chapter. One is, this is the first one children, that is the relative lowering in the vapor pressure. The first one is relative lowering in the vapor pressure. So in this, suppose we assume only solvent there in a container. If I have only solvent, it will exert its pressure. That will be referred to as the vapor pressure of the pure solvent. And to that solvent, now if I add a non-volatile solute, its vapor pressure is lowered. Why the vapor pressure is lowered? Because the solute is non-volatile. It will not go into the vapor phase. It's only the solvent which is going. So this top layer now also has solute in it. So definitely the vapor pressure by adding a non-volatile solute will lower. So you have the lowering in the vapor pressure caused by adding a non-volatile solute, right? Which we represent as, so lowering in the vapor pressure is just P naught minus P. And if I divide it by P naught, this is P naught, children. Okay. This is RLVP, right? So if it is RLVP, that is relative lowering in the vapor pressure, we represent as P naught minus P by P naught. This is equal to RLVP, relative lowering in the vapor pressure, right? So this is P naught again. So this is equal to mole fraction as per Raoult's law. This is a Raoult's law for a non-volatile solute, which says P naught minus P by P naught with reference to the pure component 1 is equal to the mole fraction of the solute. Obviously, when I add more amount of the non-volatile solute, the lowering will be more, because non-volatile solute is not going into the vapor phase. Fine. So you have this formula, P naught minus P. We'll be using this formula for numerical, children. P naught minus P by P naught is equal to W by M into M by W. Right? So this is the statement for the Raoult's law. It says the relative lowering in the vapor pressure caused by addition of non-volatile solute is equal to the mole fraction of the solute. Fine. Next colligative property, children, is elevation in the boiling point. For that, first we should know what's boiling point. Boiling point is defined as that temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. Atmospheric pressure is 1 atm. So if the liquid ka vapor pressure becomes equal to the atmospheric pressure, we call it as the that temperature at which both become equal. That is called as a boiling point. Let's understand with the a graph which says, suppose a vapor pressure and temperature graph we draw. This is for the solvent and the lower one is for the solute, for the solution. That solution which is formed by adding a non-volatile solute to that solvent, right? And this is the atmospheric pressure. So that temperature at which the vapor pressure of the solvent becomes equal to this atmospheric pressure is called as TB naught. For solvent means pure solvent. So that TB naught is the boiling point of the pure solvent. And when I add a solute, non-volatile solute to it, the pressure is lower. So graph is lower. And this point is TB now. This point is when the vapor pressure of the solution becomes equal to the atmospheric pressure. The corresponding temperature is referred to as the boiling point of the solution. Okay, so there is elevation in the boiling point. That means you can check here. This is the temperature. Now the temperature becomes more. So for the solution, the vapor pressure is more than that of the pure solvent. So there is elevation in the boiling point. We say TB minus TB naught is equal to the elevation in the boiling point. Now since this is also a colligative property, we have the formula delta TB is equal to KB into M. We write like that, delta TB is equal to KB into M. Where what was delta TB? It was TB minus TB naught. Where KB is the elevation in the boiling point. This is the formula, children. This is elevation in the boiling point. No, KB is the molar elevation constant. It's a molar elevation constant which is also referred to as ebullioscopic constant. Ebullioscopic constant. And it depends upon what is the solvent you take. So different solvents will have a different value for the KB. Okay. If unit we have to see, we can check from here. You can have KB. KB is equal to delta TB by M. Delta TB unit is Kelvin and this is moles per kg. So that goes in the numerator. It becomes Kelvin kg per mole. This is the unit for KB. Right? So you don't have to learn the values for KB. It will be given in the question. Right? So you have that final formula. If I open up this molality, you'll have this delta TB is equal to KB into weight of solute by weight of the molecular weight of the solute, weight of solute by molecular weight of solute into 1000 divided by weight of solvent in grams. It's solvent, children. Right? So next colligative property is, the depression in the freezing point. For this, even we have to talk about what's a freezing point. Freezing point is that temperature. It's that temperature when the vapor pressure of the substance in the liquid form becomes equal to the vapor pressure in the solid. So means the vapor pressure of the solid form becomes equal to the vapor pressure of the liquid form. It's called as the freezing point. Let's see in the graph. This is a graph for the solvent. It's a liquid solvent. Lower the temperature, the vapor pressure of the solvent will decrease. It will go on decreasing. At this point, that liquid solvent solidifies and now it's in the solid form only, but still by lowering temperature the vapor pressure lowers. So this is that point where the liquid and solid solvent of the vapor pressure becomes equal to the atmospheric pressure. I mean both are equal. Vapor pressure of the solid and the liquid become equal. So this point is referred to as TF naught. It's a freezing point of the pure solvent. I've not added solute to it now. Now when you add a solute, it becomes a solution, its graph is lower. So this is the point where the vapor pressure of the solid solution becomes equal to that of the liquid solutions. So that is TF. So there is depression by adding the non-volatile solute to it. So you have the graph for it, right? And TF naught is referred to as the freezing point of the pure solvent for the solution, and you get the formula delta TF is KFM. So wherein you can write TF naught minus TF, because pure solvent is more than solution. It's equal to KF into molality. You can now open up the molality and get that final formula. KF into W by M. W by M is for the solute into 1000 divided by capital W is for the solvent weight of solvent in grams. Right, so we'll use this formula also for numericals. The next colligative property, children, is osmosis. Osmotic pressure basically. For that, let's understand what's osmosis first. It's a process of movement of solvent through semi-permeable membrane from a region of lower solute concentration to higher solute. Mind it, children, go wrong here. It's lower solute concentration to higher solute concentration, right, through a semi-permeable membrane. Now what's a semi-permeable membrane? A membrane which allows only the solvent molecules to pass through it, through which only small molecule like water can pass, but not the solute molecule. They cannot pass through it. Examples for the semi-permeable membrane: pig's bladder, parchment paper. Synthetic membranes can be the cellophane. Okay. Now let's see the example for osmosis. You take a container in which solvent is outside. It is a thistle funnel. In the thistle funnel, the solution is taken. And there is a semi-permeable membrane here. So you mark the level here when you just immerse the thistle funnel in it. And after some time, what we find is the level in the thistle funnel rises because of osmosis. Solute concentration is low outside. So from here, it will go inside through osmosis and the level in the thistle funnel will rise. We can take another example for it. There are two containers. In one you take solvent, another one you take solution. They are separated by a semi-permeable membrane. Initially the level will be same in both, but after some time this level will rise. Solution side mein level will rise because of osmosis. Low solute concentration to high solute concentration, because here I took a solution along with solute. It will rise here. But suppose I don't want that osmosis to occur. So I'll have to apply a pressure here. On the solution side, the pressure has to be applied so as to stop the process of osmosis. That is called as osmotic pressure. We represent osmotic pressure by pi. So what is osmotic pressure? Defined as the pressure applied on the solution side so as to stop the process of osmosis. Okay. Now children, osmotic pressure is also a colligative property. It will also depend upon the number of the solute particles. So here we say it's proportional to the molarity of the solution. We give the formula as pi is equal to CRT. C is concentration. So we can open up concentration as molarity, basically number of moles by volume, RT. Number of moles further expanded, so we'll get N instead of N, weight by molecular weight, V and RT. So you have this formula, pi is equal to WRT by molecular weight of the solute into volume. So this is number of mole of solute, which divided by volume becomes solution concentration. Okay, so there is one reason question asked here that osmotic pressure has the advantage over the other methods for measuring the molar masses. Basically, all colligative properties help us in calculating the molecular weights of the solute. These are the formulas, children, we use. Relative lowering in vapor pressure, we can calculate molecular weight of solute. Elevation and boiling point, we can calculate molecular weight of solute. Depression and freezing point, we can calculate molecular weight of solute. Osmotic pressure, we can calculate molecular weight of the solute. So basically all methods help us in calculating the molecular weight of the solute. But what I am saying is osmotic pressure method has the advantage over the other methods to calculate the molecular weight because it uses concentration instead of molarity. Okay, it uses concentration instead of molarity. And another thing is, in comparison to the other method, its magnitude is large. And this technique is also useful for determination of molar masses of macromolecules like protein, polymers, biomolecules, etc. Because this is usually carried out at the normal temperature. At one temperature, there is no temperature variation in it. So, in these cases, that is polymers, proteins, macromolecules, they are not stable at higher temperatures. So, at normal temperature, we can calculate their molar masses easily. There is no temperature variation. So these are not stable at higher temperatures. And polymers, they have poor solubility also. Another thing better here is isotonic solutions. Isotonic solutions are those which have same osmotic pressure. Same osmotic pressure. So there is one important thing, that is blood is isotonic with 0.9% NaCl solution. Blood is isotonic with 0.9% weight by volume NaCl solution. That's the reason why this is used, for for saline solution. This is used for injecting intravenously, right? Because it's isotonic. Otherwise, there will be shrinkage or maybe swelling up of the blood cells. Okay, this I'll just explain it here. So further it says that if the blood cells are placed in a solution containing more than 0.9%, means more than 0.9 if they are placed, then the water will flow out of them and they will shrink. Okay, such solutions are hypertonic. If the blood cell is there and it is put in a solution which is more, inside is 0.9, that is blood, right? Outside, suppose it is 1.2. So solute concentration is less here. So it will go out and it will shrink. And in case it is placed in a solution less than 0.9, that is hypotonic solution, in this case it will swell. So likewise, if you have this blood cell placed, that is 0.9% is blood, and suppose it is placed outside as say 0.7%. So solute concentration is less here. This will go inside and the blood cell will swell. Both the conditions are harmful. Now children, the applications of osmosis. These are some applications. Raw mangoes, when placed in salt solutions, they shrink, they shrivel, and pickle is made in this manner. And wilted flowers revive when you put in fresh water. People who take a lot of salt, in them there is water retention. That swelling thing is called as edema. And water movement in the from the soil to the plants, that's also because of osmosis. And preservation of meat by salting, and fruits by adding sugar, that is also one of the application of osmosis. Next thing is, children, reverse osmosis. Now reverse osmosis is like earlier I told you what is osmotic pressure. Initially they were of the same level, and if I apply more pressure here, that is the atmospheric pressure plus extra pressure if I apply, that is osmotic pressure, the process osmosis stops. That is osmotic pressure. But now suppose I put here the pressure greater than, the pressure is applied here greater than the osmotic, P dash I am applying. P is atmospheric pressure, pi is osmotic pressure. If P dash is applied, which is sum of this greater than that. So P dash is applied which is greater than the osmotic pressure. Okay, osmotic pressure was just to stop the process of osmosis. If greater than that is applied, reverse osmosis will occur. Means from sea water side, the water will start flowing the other side. That means from high solute concentration to low solute concentration, the osmosis will occur. That is reverse osmosis. That's a very important technique, children, these days to extract water from seawater. That is desalination of seawater. That can be done by reverse osmosis. Next, children, is abnormal mass, abnormal molecular mass. Abnormal mass is in case the compound undergoes association or dissociation. Right? So, if there is no association or dissociation, we do not include this factor. If there is association and dissociation, we'll have to include this I factor. That is, the Van't Hoff factor. Now, what is it? I is written as normal mass by observed mass. And it's also said as observed colligative property by calculated colligative property. Let me explain it. Now, just see here, I'm taking association and dissociation. Association means small particles combine and become one. So this is your normal mass and this is what you are observing. And I told you I is normal mass by observed mass. Normal mass is less. Each particle, if I say the mass is less, observed mass is more. So I in association will be less than 1. In association, I will be less than 1. And in dissociation, what will happen? This is normal mass and this is observed. Observed mass is less. Observed mass is less or normal is more. So I is greater than 1. In dissociation, I is greater than 1. In case there is no association, dissociation, children, in that case, I will be equal to 1. So usually we do not consider I if there is no association, dissociation. Okay, but in case a compound undergoes association, we have to include this Van't Hoff factor. We can also take in terms of the another formula which I told you, the number of particles after by before. After is in the numerator, number of particles after by number of particles before. This is I. Okay. So number of particles after are becoming less. Before are more. So I is less than 1. Okay. Same way here in dissociation. Number of the particles after are becoming more. So I is greater than 1. So in all these cases, we will be, including I now. This was the first formula, colligative property, relative lowering in the vapor pressure. Same formula included I. Elevation and boiling point, I included I. Depression in freezing point, I included I. Osmotic pressure, I included I. Now, if the substance undergoes complete dissociation, I is equal to the number of the particles formed. I is equal to the number of particles formed by them. For example, NaCl. NaCl ionizes to form 2 ions. So if it is ionizing completely, 100% dissociation is there. For this, I will be 2. MgSO4 will be 2 because it forms 1 magnesium and 1 sulfate ion. KCl is 2. Potassium sulfate will be 3 because it forms 2 potassium ions and 1 sulfate ion. Potassium ferrocyanide will be 5 because it forms 4 potassium ions and 1 complex ion. FeCN taken 6 and 4 minus. So total 5. 4 plus 1, 5. Right. Suppose it says this is not 100% dissociated. Then the degree will be given to it. So you'll have degree of, alpha if I say, suppose I'm writing in terms of degree of dissociation. If the particle is undergoing dissociation, the degree of dissociation will be written as alpha is equal to I minus 1 by n minus 1. This will be a formula. For example, I is the Van't Hoff factor which we will be solving. N is number of the particles formed after dissociation, and alpha will be calculated, and whatever, sometimes the degree of dissociation they are telling you. So you'll have Ka is equal to alpha square C. Sometimes alpha is given, I is to be solved, and then some colligative property is to be calculated. Okay, and in case it is talking about the degree of association, if it is talking about degree of association, then you will have that formula alpha is equal to I minus 1 by n minus 1. 1 by n because it is decreasing. This is number of the particle, I is the Van't Hoff factor. Now some important questions I'll be discussing from your NCERT. where usually children go wrong. KH is to be calculated. This is Henry's law question, children. So you'll have the formula P is equal to KH into chi. They are saying this much molal. So you'll open this up first. This says 0.195 moles is there in 1000 grams. 1 kg solvent, 1000 grams water. So this moles is given. This is weight of solvent, 1000 gram. So with this you can calculate the mole fraction. KH is to be calculated. So STP means the normal standard pressure. Okay, 1 atmosphere pressure you can have. So P is equal to 1 and KH is to be calculated. What is chi? Chi will be written as 0.195 moles divided by 0.195 moles plus moles of water, that is 1000 divided by 18. So you will substitute this chi here. This is known and KH can be calculated. In this question, children, same way KH is given, amount is to be calculated, pressure is given. So pressure, the formula is this, P is equal to KH into chi. You know P is given as 2.5, KH value is already given. Mole fraction you will have to calculate. So mole fraction we'll open this up first. This is basically mole fraction of CO2, which is number of moles of CO2 divided by moles of CO2 plus moles of water. Moles of CO2 is to be solved. Moles of water, it is 500 ml you will take as weight of water only. I mean density of water is 1. So it is 500. 500 divided by 18, that will be the moles of water. So this is moles of water, this is to be solved. So you can put it here, either you first calculate chi from here and then separately calculate it. KH is given, this is given. Chi you calculate and separately calculate the moles of CO2. Another question, children, where normally you go wrong, P naught, PA naught, PB naught is given. Right, they are asking you to calculate the composition, means chi, and also in the vapor phase. So first the formula which you are applying is P is equal to PA naught into chi A plus PB naught into chi B. Right, P is given 600, PA naught, PB naught, they are given to you. What about the mole fractions? The two mole fractions both are unknown. So instead of using chi B, you use here formula as 1 minus chi A. Okay, instead of chi B, use 1 minus chi A. First you calculate chi A and then chi B can be calculated as 1 minus chi A. Calculate chi B. After you calculate them, they are also telling you find the vapor pressure, composition in the vapor phase. That means you'll have to first calculate separately PA and PB. PA will be equal to PA naught into chi A. Calculate this separately. You calculate PB. PB is equal to PB naught into chi B. And then total pressure you know, that is 600. The mole fraction in the vapor phase means PA by the total pressure, that is 600. Same way for the next one, PB divided by the total pressure. Right? And another question normally children are not able to do is this, calculate depression in the freezing point. Beta Ka is given, means you are supposed to consider Van't factor in this. Using this, 32 question from your textbook, using this, first you have that formula Ka is equal to alpha square C. Alpha square C. Ka is given. C you can calculate from weight, molecular, given weight of the solute, molecular weight of this, weight of solvent, calculate concentration, that is molality, use that as concentration. C. Alpha you calculate, first step. Calculate alpha. From the alpha, you will calculate I. Okay, Van't factor. Formula is I, I'll write here, I is equal to alpha. Alpha is equal to I minus 1 by N minus 1. Alpha is calculated, put here. I is to be solved. N for all these acids, will be 2. Because they ionize as CO minus and H plus. N value will be 2. I calculate I and then you put it in that normal formula of depression and freezing point. That is delta TF. This one. Delta TF is equal to I into KF into molality. KF is given, substitute. I you have already calculated from here. M molality, which you can solve. Right? Another question beta you go wrong here is this one. They are saying calculate osmotic pressure. Volume is given this much gram of potassium sulfate, assuming completely dissociated. Many of the time children forget to use I in it. It's saying completely dissociated. You have to use I value as 3. So you'll be using formula pi is equal to I into W by molecular weight into RT by V. Pi is to be solved. I will be potassium sulfate के लिए 100% dissociated. 3 weight is given. Weight of potassium sulfate is given. And molecular weight you can solve potassium sulfate. R value liter atmosphere 1 means 0.0821. Temperature convert in Kelvin. In delta TF and delta TB you don't have to convert in Kelvin because they are already talking about difference. Here you have to convert. Volume is given in liter. Directly you can use in liter and solve it. Please try solving all the questions from your textbook. Apart from that, also practice previous year questions. That only will give you, a full confidence. Okay, if you are having any doubts, you can just put it in the comments. I'll definitely solve it. Thank you for watching.